So this is now the option B, and I would like to show something about sorry. Okay, this is about option B. I would like to talk a little bit about modeling future climates and landscapes. You already know this figure, just a reminder, we want to go from present to future conditions. And here we had these two options. A, the analog approach, what we discussed before, and now the dynamic analysis of the climate and the landscape. And an example of that is described in these two publications and reports. And if you look at these publications, you will find also more references. There's a lot of material, in particular, on this option. And this example is taken from the safety assessment of the Swedish facility for high-level radioactive waste. Yeah, and this facility is constructed or will be constructed in Sweden, in Forsmark. This is at this orange part, and Forsmark is on the coast of the Baltic Sea, a bit north of Stockholm. And now you see a picture of the area. So it's really on the sea. And here you see something about the general design of the facility. We have the spent nuclear fuel in copper canisters. They will be surrounded by bentonite clay and deposited at a depth of about 500 meters. The host rock is granite, and this granite is water saturated. That's why we have these copper canisters to avoid leakage of the radionuclides in the canisters for long-term isolation. This site is a bit special because the development of the landscape is ongoing. As I said, the site is at the shoreline of the Baltic Sea. And since the end of the last ice age, which was about 12,000 years ago, the land is lifting. The current lift rate is about 6 millimeters per year. And as a result, on the long term, areas on the shoreline will dry out. These areas are, to some extent, underwater now. And then the area will develop in the order from the sea to a lake, to a wetland, to a peat area, and then to agricultural land. And due to the lift rate, which is known, the land will continue to develop as in the last 10,000 years. The reason for this lift rate is 12,000 years ago, there was a glaciation. Scandinavia was covered by a thick ice sheet, and the ice melted away. And that's why the land is rising, because these huge ice masses are gone away. Here you see a development of this landscape. You see the rise of land, and it's a change of topography. If you look at 3,000 years after the ice age, most of the part was still sea, in the Baltic Sea. 5,000 years, so you have about half terrestrial and aquatic areas, and 10,000 years, which is now we have only terrestrial parts, and this will continue. Yes, again, you see the development of the landscape. I mean, you have the sea. If you start in the left lower corner, the sea may develop to when the land is rising, to a semi-enclosed bay, to a lake, to a mire, or to a peat bog with organic soils, and to agricultural land and forests. And this development can be observed since the last millennia. This means this is a part of this area. This makes the safety assessment very complex and difficult. In this area, you see in the lower part, in the granite, you see there's a scheme of the disposal area, and due to cracks or low path space or hypothetical path space, these radionuclides may appear in the environment. Usually it should not, but assumption has to be made that it could happen. And this yellow part is a discharge point in the environment. And as you have different types of ecosystems as forest, mire, lake, stream, agriculture, you may have different implications and different doses to people if the radionuclides come to such a landscape element. Here you see this is a scheme. The dark blue one is the repository and the limits of the repository, and the red dots are the discharge points. And here you see the predicted charge point and where radionuclides might enter the biosphere. And in some of these places today we have still the sea, but in 1,000 years or 5,000 years there may be land or pasture or whatever. Here you see a scheme of the underlying radionuclide model. Radionuclides come from the underground, they migrate through the rock, they come to the deep soil, to the soil, and to the litter you may have producers, and using the soil for agriculture may cause dose to people. Or also see aquatic pathways, you have migration to the rock, then to the sediments, to bottom sediments, to water, and if you grow fish or something like that, it may cause a dose. This water may also a well may be drilled in this environment, destroying water from the aquifer and using this for irrigation. So for this system, a number of exposure scenarios were established, and specific exposure scenarios have been developed for the land use at the discharge points, considering sea, the lake, the peat bog, the forest, and the agricultural land. And it is assumed that people produce and collect food in these landscape elements, and there may be also some external exposure when people are staying in these contaminated areas. Here you see two reports describing the dose calculation in detail at the forest mark site. I think this lecture is not appropriate to go into all these details. It follows more or less similar approaches as we have discussed before. And for further interest, I would really like to refer to this one. It also includes the processes, irrigation, reception, root uptake, migration, etc. Here you see a nice picture of all the exposure pathways. You have the crop ingestion, meat and milk, hay production, also wild animal game production, use of fertilizers, etc. This follows a typical radioecological model, taking into account all the relevant exposure pathways and transfer processes. Here is a table which exposure pathways are considered for which ecosystem types. For example, for the agricultural land, there is external from the ground. We have first ingestion of cereals, of meat, milk, mushroom, fish. For the sea, of course, you have only ingestion of fish, or the same as with the lake. So again, the exposure pathways taken into account should be consistent with the characteristics of the ecosystem. Okay. This was about the development of the landscape and how these developments in landscape are addressed. Now we come to the climate. So in the climate, there were four main elements, four main steps. Everything started with the analysis of the past climate. Then it was explored the implications of the greenhouse effect and global warming. Then comes the important point, it's a difficult point about the extrapolation to the future and exploring a range of climate paths. So the climates considered in the safety assessment for the Swedish waste disposal facility are the following. First of all, global warming. This means we have temperate conditions until 50,000 years after present. And after this, we have a natural variability, cooling of climate until 100,000 years after present. Then it's the early burial glacial. This means we may have an ice age earlier than the normal cycle of ice ages would make you expect. It's the same as a warmer global phase, but for a period of 3,000 years, there are very glacial conditions at about 17,000 years after present. And the extended global warming is we have temperate conditions until 10,000 years, 100,000 years from now. And the last one is a Weichselian glacial cycle. It's a repetition of the glacial cycles as we have observed in the past. This is a simple extrapolation of the conditions in the past to the future. You may remember this curve where you have seen the temperature in the last 400,000 years. And this is the last one is a repetition of that. And here you see the average temperature at Forschmark for these different cases. You have the green is global warming, red is extended global warming, so the temperature stays higher, and the blue line is early ice age, so you have a drop of temperature after 10,000 years and it goes up again. I mean, of course, all these predictions, all of these assessments they are based on both the development of the climate in the last 400,000 years or longer, the last climate cycles, in addition to some assumption about global warming caused by emissions of carbon dioxide. I mean, there's some plausibility. I think this is about the range which it could happen. However, predictions to the far future, in this case, are always are not without problems, because it's very difficult to validate. And in so far, these two options which I have shown you, with this dynamic modeling on the one side and the analog approach on the other side, complement quite well. Okay, here's a report where all this is described in detail. And what they have done if you look at the left side, there's a green box which says main safety assessment scenarios. These are the scenarios which are considered as most important. But to complement this picture, they have also used some residual scenarios as extended global warming or the normal glacial cycle. So you see what they did is also they tried to find an envelope of the developments that might occur in the future. And here, this is just a scheme of a scheme for the safety assessment, how these two elements of changes of landscape and change of climate come together. On the bottom, you see the development of the landscape, and this is linked to the development of the climate in the next 120,000 years, and then this comes up to an risk assessment. And I mean, this is all indicative, and this figure on the right lower corner gives you the sievert per year, per becquerel per year released. Or the first phase is temperate climate, etc. Here this picture is a bit clearer. This is a simulation of the doses per unit activity released for a biosphere object since the last ice age. So to say, to look backwards, what was the development in the last years. So it assumes that the discharge has happened 9,000 years ago and is still ongoing. And if they look at the this famous radionuclides, is selenium-79, iodine-129, neptunium, radium, chlorine, and cesium-135. The left blue part means it's still under the sea. The dischargement is under the sea. You see also the time where we are today. This is about in the middle of this graph. And then we have a white transition period, a lake stage, and a terrestrial stage. And this is how these radionuclides enter at these different stages of the landscape. You also see that in the sea, the seaward or this dose, the potential dose is relatively low. So the more critical parts, landscape objects, are the lake or the terrestrial areas. Okay, so this is an overall prediction. This is the overall prediction of doses due to release from the repository for high-level waste. So you see the dose criterion is 15 microsievert per year. And on the right side, you see all the radionuclides which are considered in this study. So it's a big, very difficult to differentiate. But if you look at the upper black area, then you see that the doses in this case is less than 10 microsievert per year. Okay, and that's already it. And we have also a summary for this option B, dynamic modeling of landscape and climate. It is obvious that environmental change is driven by climate and topography. The climate is modeled based on an analysis of past climates, on the greenhouse effect, and then these data are then used for an extrapolation to the future. The topography changes due to an annual uplift, and therefore we have the development from sea to lake to wetland to peat bog and to agricultural land. The models reflect many interactions. I could not go into the detail on that, but we have seen that there's a difference, interaction between climate and hydrology, between landform and hydrology, and also between the release of radionuclides from the geosphere to the biosphere is also taken into account. The assessment of radiation doses is based for each landscape elements, and the migration within these landscape elements is taken into account, causing an accumulation of radionuclides and land use come up with a dose to people. As you can imagine, this approach needs enormous amounts of data to quantify all processes and also to model future climates and future landscapes. So that means it is more complex than this analog approach which I have presented before. However, I mean, the land lift model can be validated relatively easily due to the past development. However, predicting future conditions for the climate is always a bit as a speculative element. However, this speculative element can be overcome if more climate pathways are taken into account, as it was done by the Swedish colleagues. Okay, then thank you very much.